Okay. Okay, so it's a real pleasure to introduce you today Hanna Übler. She did her PhD back in MPA, working already on integral fluid spectroscopy of high redshift galaxies. Indeed, she is really an expert on galaxy evolution, also including AGN. Then she moved to Cambridge, working with the team of Roberto Maiolino and the JADES collaboration in general. So, of course, she used extensively JWST observations, and now she has her own group at MPE in Garking that she's leading, and she will talk about observational constraints of massive black holes in the first few billion years. So, thank you very much, Hanna, and the stage is yours.
Thank you very much, Roberta. Yeah, it's really my pleasure to be here. Thank you for the invitation to come. It's my second time in Ljubljana. I think I was here as a kid for vacation, so a long time ago, and so it's nice to be back here as a grown-up, and of course also to come for a scientific visit. So I will talk a little bit about some of the recent constraints that we learned about massive black holes in the first few billion years, and most of what I will talk about today has been done in collaboration with the NIRSpec GTO teams GA-NIFS and JADES. So GA-NIFS is an IFS GTO, and JADES is a joint GTO of the slit spectroscopy with NIRCam. And then also at the end some results from a new large program in the IFS that we are conducting this cycle. So just to set a little bit the stage, here we have a schematic view of the evolution of our universe, and of course we have different observational tools available at our disposal to study galaxies and also study the evolution of galaxies by looking at objects that are farther and farther away. Now, we've learned a great deal in the past decades about how the general properties of galaxies have evolved in the last couple of billion years through these surveys. For instance, we know that there has been a peak of star formation rate density in the cosmos roughly around redshift 1 to 3, so this is sometimes called cosmic noon. And the recent wind down of star formation in the present day goes together also with the winding down of the available molecular gas fraction within galaxies, which of course is the fuel of star formation. And at the same time, the galaxies are growing in mass and in size. And one other interesting quantity that is telling us, or is used to tell us about black holes, is the black hole accretion rate density. So this is also overplotted here in this plot of the star formation rate history. And you can see that while the normalizations are different, this has a very similar shape to the star formation rate history. And so this evidence, together with what we know from the local universe about black holes and galaxies, which you can see here, black hole mass as a function of bulge mass. This is for early type galaxies, so this is basically the total stellar mass of the system. You can see that there's a fairly tight relation. And so this evidence in local galaxies together with this evolution here has suggested early on that there is sort of a co-evolution of the central black holes in galaxies and their galaxies altogether. Now, I will tell you, and many of you are working, of course, also in this exciting field, so you also know from your own work that recent observational results from the James Webb Space Telescope start to challenge a little bit our understanding of this co-evolution. But actually already before the advent of JWST, there were indications that in the early universe this sort of co-evolution picture of galaxies and massive black holes could have been breaking down. So this is a plot from a review by Xiaohui Fan and collaborators in 2023. And this does not include any JWST data on purpose. So the red points that you see in the upper plot here, we have again black hole mass as a function of age of the universe. So you can see that there are several sources above redshift 5, so well in the first billion years of the universe, that have black holes in excess of 10 to the 9 or so solar masses. So very, very massive black holes very early on. And so already at the time, people started to explore how you can grow these black holes. And so this is something which now has received renewed attention through the results that we are getting with JWST.
There is a pointer.
Ah, perfect. Yes, these are the ones that I like. Excellent. Okay, thank you. Okay, so What JWST now brings to the picture is when we focus here on the time frames where we can observe galaxies. With ground-based spectroscopy, because of the Earth's atmosphere, we can only sort of study a limited epoch of the history of the universe if we are interested in, for instance, the rest frame optical and rest frame UV lines. Now with ALMA, we can already push a little bit further, as you've seen, and many of you are also working on this. And now with JWST, we can really push well into the first few 100 million years of cosmic time and extend our studies, especially of the rest frame optical regime, into much earlier times. Now, many of you are familiar, of course, with James Webb. Just for those of you that maybe do not work on this, what you see here is a focal plane of JWST, and you can see the different instruments. You have NIRSpec, NIRCam, MIRI, and NIRIS. And I will focus on results that we got mostly with NIRSpec. So what you can see in these large quadrants here is basically light falling through what is called the multi-shutter array. So this is an array of slitlets that can be opened and closed, and you can observe up to about 200 objects at a time without any spectral overlap. You can also open everything, but then you have to deal with background subtraction and see how you separate your source from other sources. Then there are some fixed slits that I'm not sure if you can see on the projector, but then there's a different instrumentation mode which is called the integral field unit. And this is a zoom in here. So this is a fantastic instrument. It's very small, but allows us to do some great science, as I will show later. This is 3 by 3 arcsecond, has a nominal spatial resolution of 0.1 arcsecond, so that's similar to the NIRSpec slit nominal resolution. And again, here we have 3 different resolution modes, low up to moderately high resolution. So 2700 is the highest resolution mode. Now, of course, from the ground, we can get much, much higher resolution, but we are, of course, limited in the wavelength range that we can observe. And so from space, this is the best that we can do in this wavelength range, 0.6 to 5.3. A few words about these GTO surveys before I go to the science results. So we have on the one hand JADES, as I mentioned already. This is a joint GTO of this slit spectroscopic multi-slit mode in NIRSpec and NIRCam imaging. So in the background, you can see an image from the survey which is called JADES, where you can really appreciate all of these fantastic individual sources that are in there over all of cosmic time, what we can observe in the steep fields. And so here, the strategy is that we get this imaging, we can do targeted spectroscopic follow-up. Many targets were also, of course, selected in the first cycle based on HSD imaging and so on. And here we can really try to get sort of a statistical view on early galaxy properties and their evolution through thousands of spectra that we are getting and through all of this imaging. Now, on the other hand, in the IFS, we have a very different approach. Most of the targets have been selected, of course, before any JWST data was taken. With the IFS, we can only observe one object at a time, so you have to very carefully select what you want to spend your time on. Then you need several hours for each object. So here we have objects that were selected before, known for their, for instance, Lyman alpha properties, that were known from ALMA, and some that were known from ground spectroscopy with, for instance, X-shooter also. You have, of course, to know the redshift here precisely, otherwise you waste a lot of precious telescope time. And we are observing the objects in high and low resolution for most of them for several hours, as I mentioned. Then in the cycle that is ongoing at the moment, we got some more time that was carried over. And so here we could select a few more objects already based on some JWST data that we had available. And of course, a variety of science topics can be targeted with these different surveys. For the talk today, I will focus mostly on the black hole properties, but of course there are many papers out as well that focus, for instance, on the interstellar medium of these galaxies, on kinematics, and so on. And also in JADES, of course, there are many, many papers that don't deal with AGN, but focus on the physical properties of galaxies in general. Now, I will mostly talk about the IFS survey, which is a bit closer to my heart, but I want to just highlight, of course, from JADES some of the results that are really outstanding, and one of them is the currently highest redshift detection, spectroscopic detection of a galaxy. So this is roughly redshift 14.3, here detected just by the Lyman alpha break. You can see otherwise the spectrum here looks fairly featureless. Through some new data and improved reduction, we also have line detections now in this object, and it has been followed up with ALMA as well in some of these papers where there has also been a spectroscopic line detection. You can see that this is, in this image here, this red object, there's actually a foreground galaxy, so it was fairly challenging to properly separate the spectroscopy here, but there are of course ways to do it, and this is of course fantastic to have such a distant object, and we expect with all of the different surveys that are ongoing in the GTO in the open time, we will be able to push further to even earlier cosmic times. There are several photometric candidates at higher redshifts available, and so of course everybody is busy in trying and follow up and try to find an object at even earlier cosmic time.
Did the redshift stay the same? I mean, how well did you determine redshift just from the continuum?
Yeah, so this was, just with this is a little bit uncertain indeed. And so the redshift that is listed here for 14.32 already changed a little bit through the detection of the emission lines then in ALMA. I think it now is around 14.2 or something like this. So it was a significant change, but not still, let's say, both of these numbers are roughly 300 million years after the Big Bang.
I'm asking because we have similar objects.
Yeah.
We were wondering, you know, how much.
Yeah. So this, of course, depends on if you just determine from the modeling of the damping ring, and the emission lines give you a much better constraint than also on the column densities and so on. Now, in terms of AGN, one interesting object from the JADES survey is GNC11. So this was a galaxy that was already known before the launch of JWST to be at very high redshift. Therefore, its name 11, while the actual redshift is 10.6 or something like this, which was then spectroscopically confirmed. And here you can appreciate that if you look at the spectral shapes, they are very different. So where you just see a fairly featureless spectrum over here, now just a little bit later in cosmic time in this object we see very strong emission lines, and they are actually extremely useful for us to determine the physical properties of these sources. And specifically for this object, they helped us also to constrain the central energy source in the system, which we think is an AGN, based on several indicators. So on the one hand, you can see this is a very compact source. This is almost consistent with the point source, although we see some extension in the photometric modeling. But then we also have several interesting emission lines that we can study. And we have a couple, like here, these nitrogen multiplets that are, for instance, sensitive to density. So certain transitions are suppressed compared to others. And here we can constrain that the density in this gas that we are observing is extremely high, above 10 to the 6, maybe up to 10 to the 10. We also see some features where we see fairly fast outflows. This is not extremely high, but a few hundred kilometers per second. And then we also have some very high ionization lines, like these neon lines over here. And so taken together, this suggests to us that we have an active black hole in this source. Now, these are just individual objects that I showed you, but of course now the power of JADES, as I mentioned at the beginning, is to get us some more statistics. So this is an overview of bolometric luminosity as a function of redshift, and what you see here in brown is AGN that were known before the launch of JWST, and all of the blue symbols are now AGN that have been newly identified. So of course there are also JWST observations in these regimes, but they are not shown on the plot here. These are just newly discovered objects. And so what you can appreciate here, that JWST helps us to push down in luminosity, but also to push to higher redshifts in the study of these early accreting black holes. And we are still in the process to assemble statistics. At the moment, we would say that about 10 to 20% of galaxies in this redshift regime here, 4 to 6, appear to host one of these moderate luminosity AGN. This is how many of these objects look like. Of course, many of you know and are also working on this. So many of them appear fairly compact, of these actively accreting black holes. Many of them have somewhat reddish colors, and there is this terminology of the little red dots that I know you're also much involved in. I just want to emphasize that while many of the little red dots, when they are spectroscopically followed up and confirmed, really appear to be broadline AGN, but we also have many AGN that do not fall into these characteristics of the little red dots at high redshift. So we think that only about, from the current numbers that we have, maybe 30% or so are actually falling into these characteristics of the little red dots. Now, it's a little bit also complicated or challenging to follow this field. There's a lot going on, many papers out every day and different definitions of what the little red dot is. So this also depends a lot on which paper you look at, okay? But just to caution that there are, while this is of course a very exciting field, there are also AGN that do not fall into these characteristics. What's also interesting is that many of these sources appear to have some blue stuff around them fairly close. Now, only with photometry, you don't know whether this is at the same redshift. So here, of course, you need the spectroscopy. And indeed, we could find that many of these surrounding sources are at a similar redshift or at the same redshift. And of course, this could be signs of accretion onto these objects, which might fuel the activity of these black holes. And that's a very interesting field that at the moment has not been statistically approached, I would say. So that's an interesting something where I think we will learn more in the coming years with the data that is now available. Now, this is an example spectrum of one of these objects. You can see it up here. Also here, I'm not sure whether you see with the projector, there are some different colored... This is not lensed. Oh. Some different colored fluffs around. And indeed, we found through the spectroscopy that these are at the same redshift. Yeah? Now, the spectrum that you see here is just extracted from the very central source. This is in log scale, the flux, so the signal to noise is extremely high in this object. And we go to the log scale to see the faint lines and to actually constrain the noise. And here you can see that we have these broad line bases in the hydrogen and in the helium lines. And this is indicative of the very fast motions of gas swirling around a central black hole. So this is how we determine that we have a black hole in this source. We also see some very highly ionized species. We have helium-2, argon-4, a line that I never even thought about when I was working with ground-based spectroscopy. So this is density sensitive. So I was very excited because when I was working mostly with ground-based data, I worked, for instance, on measuring density in the interstellar medium with the S2 doublet. And so to have something else here that you can use as well was already fantastic for me. We have some indications of iron features here, and they have been confirmed in our low resolution data where you have a higher sensitivity. Some tentative detections of coronal lines and also some unidentified lines. And so with all of this together, of course, you can constrain a variety of physical properties in the source. You can look at metallicity, you can look at kinematics through the IFU by resolving motions of the narrow lines. But of course, we are also interested in the properties of the black holes. So I want to continue a little bit on this, but before, I also want to emphasize that this is in one of the deepest Chandra fields that we have at the moment. We have 7 million second integration here and do not have a detection. And this is something that has now been seen for many of these compact AGN, that they are either X-ray weak or really do not show any X-ray. There are some exceptions, of course, that we have. Also at high redshift, redshift 10 or so, where people have found black holes actually based on the X-ray measurements. But this seems to be a characteristic of many of these early low luminosity AGN, that they are X-ray weak and also fairly radio weak. Now here is now the low resolution spectrum of the same object. And something that I'd like to point out is that when we look here in the H-alpha N2 complex, you see that we have a detection of nitrogen here, but this is fairly weak. Just remember again, we are in the log scale here. Now, when we go to the rest frame UV, you see that we have booming N2 lines, okay, not N2, nitrogen lines, as you can see also in the zoom in here. And so in this study, now combining our high resolution information with the low resolution data, Shihan Yi worked on modeling this and constraining the different properties that we can extract from the rest frame UV and the rest frame optical. And what we see in the source here, that is that we have a stratification of the medium in the source, both in density but also in the chemical composition. Yeah? And these nitrogen-rich sources have received some attention generally now in the past months in the literature. Here you can see a plot of N/O as a function of metallicity, and some of the sources that were available at the time have been plotted here. And what is really interesting, and I know of course that also some of you have been working on this, finding very high nitrogen lines in the rest frame UV. And what you have been finding and other people have been noticing is that these chemical yields that we are constraining for some of these objects are different from what we see, let's say, in typical H2 regions nearby, but are actually fairly similar to what has been found in, for instance, second generation globular clusters. And so people are now interested in constraining whether there could be more physical properties like these enrichment patterns or the densities that are similar between these different kind of sources. And so we are working at the moment with researchers in Cambridge like Vasily Belokurov in trying to further investigate this picture. Yes, Roberta source, okay. Now about the black holes, as I mentioned in the beginning, we have these broad line bases, and we can use this to constrain using what is called a single epoch method, the black hole mass. So this works in a way that there are scaling relations that have been developed on local black hole data that relate the luminosity and the width of these broad lines to a black hole mass. Now this comes with some uncertainties that we should be aware of. So first of all, also for the local universe where these relations are calibrated, there is a large scatter. So there's already about an uncertainty of 0.4 Dex or so on these masses if you take this into account. But there are also other concerns that have been raised since now this data has been popping up more and more, whether these single epoch methods are actually applicable to these high redshift black holes. Now, for instance, in this case, for the luminosity of the source that we have, we are at least within the coverage of some of these locally calibrated data, so that's already helpful. But still, there are some words of caution that I think now the community becomes to appreciate, and I just want to mention some of those before moving on. So one very interesting measurement that has come out last year from the Gravity collaboration. This is using the 4 unit telescopes on the Very Large Telescope in Chile as an interferometer to really constrain very small scales for very distant objects. So this is what they did here for a galaxy at redshift 2.3, which sounds low redshift, but is very close actually to the high redshift sources that we study. So this covers most of the history of the universe already. They could dynamically constrain with the model that is shown in the plot here the black hole mass of a very luminous quasar and compare directly to the estimates from the single epoch methods. And what they were finding here is that, for instance, for H alpha, the single epoch method overestimated the black hole mass by roughly a factor 2 or 2 to 3. This was worse than for H beta, very bad for carbon 4 and some of these other lines. So this could indicate that there is a systematic overestimation that we're doing with the single epoch methods, but just with one object, of course, this is not yet constrained, and this is also accreting at highly super Eddington. And this, of course, may also play a role in the geometry of the broadline region and so on. So the team has some more sources in preparation, and so we can expect more results on this soon, but this is something, of course, to keep in mind. And I know that the team, they are now building an upgrade to this observing mode, where they will be able to look at fainter objects and at even earlier cosmic times. So more data from this program will significantly, I think, help us working on these higher redshift objects to get a better understanding on the systematics in these mass estimates.
Is there a reason you're saying that they might be all overestimated? Is it likelihood more that we are overestimating rather than underestimating?
So for this one object, they find that, yes, they find that all of the single epoch methods overestimate by different amounts, let's say. So for H alpha, I mean, a factor 2 sounds acceptable for what we are doing. Yeah, but of course, at this point in time, and with what we know from the work in the local universe about also the relevance of the Eddington accretion factor, is not yet clear whether this applies to all objects, but already provides, let's say, a word of caution on the measurements.
I'm just wondering whether we are expecting all of them to be overestimated, or is it just, you know, some of them might be underestimated too?
So this would depend mostly on the geometry of the broadline region. So this is an aspect that I will come to now. I think from what we know now, I would expect that probably they are rather overestimated instead of underestimated. So something that we explored here in a paper with Roberto Maiolino is the fact of this X-ray weakness that I mentioned at the beginning. So there are different theories how this could come about. And while we don't have a very good handle on this, of course, one possible option is that the X-rays are not necessarily intrinsically weak, but could be absorbed by very dense medium. However, this would require that this dense medium is fairly well distributed around the black hole, because we see this for so many objects. And this would indicate that if, for instance, this absorption comes about within the broadline region, means the geometry of the broadline region has to be different compared to what the local calibrations are based about, so that we have a higher covering factor. Now, if you have a higher covering factor, of course, the luminosity that you use for the single epoch methods doesn't match anymore what these are calibrated on. And so this would also suggest that black holes would be overestimated based on these methods by maybe a factor up to 3. And we have indeed more evidence that there is a different appearance of this broadline region. Of course, we cannot observe it directly with the data that we have, but what has been found first by Jorrit Martí and his team, but then later has been seen in several other targets, is that we find absorption in these broadline regions. So this is Balmer absorption that you see here and over here. This is from Ignace Jules-Barlis from the JADES team in a lower redshift object. And this suggests really that we have these very high densities. Again, to be able to see this absorption, it's very hard to populate this in a level that we would be able to see it. And we find these features now in about 10% of the objects that have been discovered. So two things I want to point out here. In the local universe, this is seen just in a sub-percentage level. That we see already 10% suggests that the probability to be able to observe this has to be higher, which again would fit with a picture where these clouds, for instance in the broadline region, are more homogeneously distributed. Then you would have a higher chance, of course, to see the absorption. And the other thing I want to point out is that we have several cases where we see this in the high resolution data, but in the medium resolution data or even in the low resolution data, this is out-resolved. And you won't be able to detect this. So we think this is really a lower limit on the occurrences of this absorption. And this would again indicate that we really may have a different structure of the broadline region or certainly of the very dense gas in these sources. Now, keeping in mind what I just said in, let's say, cautionary words about these black hole mass measurements, so far what we could determine from this gravity result or also from the consideration of these geometrical distribution is that maybe there are factors of a few by which these black hole masses would be overestimated with this information that we have. But if we look at the actual measurements, so here you have black hole mass as a function of stellar mass. This is a recent compilation by Madeleine Marshall. What you see here in green and in blue are local universe relations for these properties. JWST data here is in blue, this orange point from Madeleine's paper, and in purple. And in gray are some of these quasars that I showed at the very beginning that were already known before JWST. And you can see that these sources, when you look at the black hole mass, are overmassive with respect to these local relations by several orders of magnitude. So even if we overestimate systematically the black hole masses by a factor of 5 or even by a factor of 10, we are still in a regime where these black holes are clearly overmassive compared to their host properties. And this is what many people...
How well do we know the stellar mass?
That's a very good point. So for, I think, most of this blue data here, at least from the JADES survey, this comes from SED fitting. And this has, of course, some uncertainties that are also substantial. Now, typically, we would tend to overestimate the stellar masses, specifically because of the uncertainty of the contribution of the AGN in the fitting. So this way you would move further over there, which just makes the problem worse. But it's a very good point that you mentioned. I think the stellar masses are uncertain, and so what people have started to look into now is to not take the stellar mass, but look at other measures of sort of the potential of the galaxy, for instance, the velocity dispersion or the dynamical mass, where arguably we would have a better handle, or no, it's just a more direct measurement in the case of the velocity dispersion. And indeed, it seems that perhaps here it does not look such a dramatic difference to the local universe. And what would that mean? That means that either the stellar masses are just not accurate enough, or if they are fine, there's a lot of material not in the form of stars already present there. So of course we think that these objects are at the center of overdensity, so we have dark matter. Now the sources are very compact, so maybe the dark matter does not play such a big role really in the dynamical mass of the systems, but of course we expect to have a lot of gas to fuel the black hole, to grow over the rest of the universe, all of this mass in the galaxy. And so this could be a way to constrain the relative contributions of baryons basically in these early systems.
But can just the dynamical mass be wrong too? Because those systems are probably more disturbed,
Yeah.
Dynamical tracers might be less accurate too.
That's of course another concern. So many of the dynamical mass estimates, if you rely on just integrated line widths, they try to account for some structural factors that are very hard to measure here. But what you can do is you can explore the full range basically of these factors that you would expect. Let's say surface index between 0.5 and 8 or something like this. The sizes are fairly small, so you cannot go too wrong there, let's say. And so you can constrain something, and then you typically get maybe an order of magnitude uncertainty. But this is not so much actually when you look at these plots. Already for the black hole masses we have 0.4 uncertainty, for the stellar masses is similar. And so this, even if you know nothing about the structure, would give you a way to constrain sort of the total material in it. Now it's a different situation if you want to build a full resolved dynamical model. For this, first of all, you need to resolve the host galaxy, which is challenging. And then this could be a bit more subject to the assumptions that you make on whether the system, of course, is virialized or not. In general, I think the integrated lines give us a fairly good way to approach this. And if we see rotation in the sources, then I think we can be, can use this information, of course, to try and constrain further. But mostly, for many of these sources, I think the challenge at the moment is to actually detect really the host galaxy. And I show some examples where we can do this later on, but it's not, for many of these little red dots and very compact sources, it's not something that can be done so easily. I think I probably need to speed up a lot. Okay, so I will skip a couple of things. So what I wanted to focus on here is that looking at these very massive black holes, of course, many people are wondering how they can become so massive in such a short time. And so now many theorists and modelers are working on different models, super Eddington accretion, heavy seeds, and so on, which are now being explored with the data that the community can provide. But one channel that is also very exciting from the observational perspective is to try and look for pairs of these AGN and try to look for merging, also in preparation for the next generation of gravitational wave observatories like LISA that will then actually constrain these masses. And so here I just wanted to show you some examples from our IFS survey where with the field of view we can actually look for companions of our main sources and characterize them spectroscopically. And so in this work by Michele Perner here, he found, for instance, that the fraction of dual AGN active black hole systems at redshift 3 to 4 is already a little bit higher than what we would expect from cosmological simulations. We had one source that we were extremely excited about in the IFS, where we could detect a broadline region in an object here in a galaxy merger and constrain a narrowline AGN in the other source, where we have in velocity and spatial separation two AGN that are already very close to each other, where we would expect them to merge based on dynamical friction already being efficient in the stellar structure of the system within a few 100 million years. And so, of course, LISA will tell us exactly what are the statistics and the masses of the black holes that are merging at these times. Now, I will skip this, mostly skip it, just to point out we have these line ratio diagnostics in the local universe that help us to separate AGN and star formation as the primary photoionization sources in systems. And what we have been finding now for systems that's very high redshift, largely due to their lower metallicity, as that these diagnostics are no longer effective. So people try to explore other diagnostics. I know that also you have been working on this. For instance, Roberta has been working on this to try and identify new diagnostic diagrams that are not so impacted by these different ISM conditions and still can help us to at least identify whether we see an AGN or maybe a mixture. So if you're interested, maybe we can chat more about this later. This just to say we have galaxies where we do resolve a host galaxy and where we can do detailed kinematic modeling of the dynamics of the systems and really bring together what we constrain for the black hole and for the whole galaxy. This is, of course, the goal. We don't want to just learn about the black holes. We want to understand how the evolution of black holes and galaxies was with cosmic time, to understand more about this apparent breakup or decoupling of the growth in early history. So if you want to know more about this, we can chat later. In the final few minutes, I want to show you some of the results that we have now been getting in a large program with the NIRSpec IFS, which is currently running. So here we target 20 AGN at redshift greater than 5. We have some more in our GTO data, and there are some other programs also doing studying fewer numbers of objects with this approach. So we think that we will have around 30 or 40 or so at the end of this year, where we get now IFU data for some of these AGN that have been identified in just slit spectroscopy, exactly to try and constrain not just the black hole, but also what we can learn about the host galaxy, try to measure, for instance, accurately the velocity dispersions and the dynamical masses, and also, of course, explore the surroundings in the field of view to look for additional sources that we can spectroscopically confirm. And we are well advanced in the program. We had some solar flares and got some re-observations, because then it's a great pain to clean the data if you have all of these cosmic ray hits. And The first source that we looked at in detail is a triply lensed source at redshift 7. So this was first discovered in the Uncover survey. There are a couple of papers by Lukas Furtag and Jenny Green that study this object. And this has been peculiar because of the spectral shape that you can see here, yeah, and what appears to be a fairly smooth Balmer break. And so there have been papers trying to model this as is typically done through stellar populations. For instance, this paper here, finding extremely high stellar masses and due to the compact size of this object, very, very high stellar densities that are otherwise just found in nuclear star clusters or so in the local universe. So extremely, very extreme object. And what Shihan Yi, who led this work here, showed is that by instead modeling this through basically absorption of an AGN continuum through very dense gas, which we think we have in many of these objects, he can reproduce fairly well, especially the smooth feature of this break. And so this alleviates the need for these extremely high stellar masses and instead suggests that we have this extremely high dense, largely dust-free gas. And indeed, in our high-resolution data, so in this program I forgot to mention, we always get prism data and high-resolution data in the band 3 grading. Indeed, we saw, with not so high significance here, absorption again in the Balmer lines, which would also suggest and fits together with this model that we see this absorption. And now in a follow-up paper, Francesco Toicenio managed to expand the region from the detector where data is nominally extracted. So there are of course wavelength and flux calibrations. So he could push towards what you see here. You see here just the beginning of the H alpha line, but it's not fully covered here. So he could push the extraction of emission to recover in the high resolution grading the H alpha line. And indeed here we also very clearly see with much higher signal to noise the absorption in the H alpha spectrum, confirming these high densities that we could find. And here what we can also do now, what we briefly discussed before, is to use the narrow lines in the high resolution spectrum to get a first estimate of the dynamical mass. Of course, with the uncertainties that we discussed, but gives us some handle on it. And what we are finding here is that the dynamical mass constrained from this work, so this is, you can see the uncertainties so I appreciate already by the fact that different lines give slightly different upper limits here. We cannot fully constrain because the line widths compared to the spectral resolution are so low that with this 2700 we cannot robustly really resolve the lines. This is why we just get upper limits here. But these upper limits on the dynamical mass are already an order of magnitude lower than the previous estimate on the total stellar mass in the system when trying to model through stellar populations. Yeah? And so this is a very interesting and rich source, and we have some more work in preparation on this specific object now, but of course also on the other objects that we have in the survey. And it's really fantastic to see these results and to see now the detail that we already get in constraints on the physical properties of these sources in terms of these very high densities, especially through these absorption features. So with this, I would like to end. Thank you very much for coming and for your attention. What you should take away is that JWST provides us a way to study early active black holes in great detail and in means that were completely inaccessible before, just through the wavelength coverage that we now can get, especially in resolving in the terrestrial optical and terrestrial UV also these broad Balmer features. And just the first few years now of observations have brought forth many exciting and completely unexpected results. And I showed you a few of those, and we can expect that we will learn much more, hopefully also about these properties that are especially surprising, like this X-ray weakness, these absorption features, something that I didn't now cover in the talk, For this moderate luminosity AGN, we do see some outflows, but it's not on the level like you see in these quasars or just at cosmic noon in comparable AGN. So that's something to be investigated. And with the programs that are ongoing now, and especially also with the integral field unit that gives us this wonderful data coverage of the spatially resolved spectroscopy, we hope that we can learn much more in the coming years. So if you're interested in this topic, keep an eye out on all of the results. And of course, I know that you are also actively involved in this. So I'm also interested to hear what you will tell me later about your ongoing work. So thanks very much.
Thank you. Thank you very much, Anna. Many, many, many interesting results. Let's see if anyone has some questions.
I do.
Okay, great.
How do you get 7 million seconds on Chandra?
Oh, this I don't know. So this is ancillary data.
That's 80 days.
From the deepest fields, basically. So I think there is another large ongoing program by Andy Fabian at the moment. So this is just ancillary data that we could use. So have to ask the experts there how
it's
to.
mostly luck that your object was.
Yes, yeah, it's simply in one of these deep fields, but I think they are fairly large.
Very well studied fields
Yeah.
that everybody's using, so everybody's
And you
targeting.
stack data.
Yeah.
Yeah, this is data from multiple cycles
Yeah.
stacked together.
So there are two deep fields in Chandra, I think, the deep field south and the deep field north, and yeah. That's right. I mean, these are the classical deep galaxy evolution fields where we can leverage all of this existing ancillary data.
I have a question.
Yeah.
So you mentioned black hole mass demographics, right?
Mm-hmm.
About spins of black holes.
Yeah, so that's of course even more challenging to measure. So this is not my field of expertise. I know that already in the local universe it's not so straightforward to measure the black hole spins. There are some methods in modeling, I think the accretion flows that help you to try and constrain what would the black hole spin be. I know that there are some people in the community working on this also for the high redshift data, but I don't know what the status of this is. I imagine it must be extremely hard. Maybe for the lens sources, you can be able to provide some constraints, but for these other type of sources that I showed, I would not know how it would be possible to constrain this. But maybe you know, I don't know.
Regarding LISA, I was surprised when you said that this is something that LISA could do. I know very little about LISA obviously, but what's the highest redshift galaxy merger
Yeah, so in principle, from the current sensitivity estimates, this can go to very, very high redshift. I can check if I have, I'm not sure if I have a plot here, but we can look at it later. So the sensitivity is not the same everywhere. Basically, typically people plot a redshift versus black hole mass region. And then there is peak sensitivity in some of these regimes. And for instance, the source that I showed you, when I put it on these diagrams, is sort of at the edge, but where you still have a signal to noise of 20 if you expect a merge in this regime. So this can go, in principle, into a redshift 12 or even higher. But of course, the signal to noise will be higher for a specific black hole mass range and at somewhat lower redshifts than what we explore here, but we expect still to have sensitivity there. And what I meant with this is what it will tell us. LISA will give us the statistics and the masses of the black hole mergers. Yeah.
I mean, once you detect it, you do wonderful things. I was just very surprised that you could even go that far.
Yeah, so I think I have a plot where I show where this source would lie on such a sensitivity diagram, so I'm happy to show you later.
Can I ask about the locally calibrated relation between H alpha and black hole mass? You have an epsilon parameter in there. What is it?
Say it again?
There's an epsilon parameter, I think,
yeah.
in it.
Who should even
Yeah,
remember?
it was the next one.
Sorry. Okay. Oh, yeah. Yes, so this is what is called the virial factor. Often this is an F in the relations, and it depends on whether it's F or 1 over F, and then it's typically called epsilon, so it's not so important. But this basically, so these relations are themselves calibrated based on the size and the luminosity of broadline regions for sources in the local universe where you can actually measure this. Mm-hmm. And so there is this virial factor involved that basically already tells you something about when you plot all of these sizes and luminosities, you also have some scatter. And this, it gives you information about the geometry really of this size versus luminosity accretion disk basically. Yeah? And so this varies for sources in the local universe, this is known, and reflects in the scatter. And basically what people do here is they fit a line through the luminosity radius, adopting an average virial factor that people are using. So I think in this case is something like 1.07 or so. For the measurements that we did here, for instance, I took this into account by taking the range of the virial factors and folding this into the uncertainties. Yeah? But still, you are dominated by the scatter that is just in the local relations already. Yes. So what goes into the uncertainties here is really just the scatter. Even if you fold in all of these uncertainties and all of these parameters, you're reaching maybe 0.1 or 0.2 for the high signal to noise data that we have here. But there is a lot of uncertainty in, or not uncertainty, there's a lot of scatter already in the local data. And so one has to be mindful of that, I think, in the measurements.
I think very naively that if you have an AGN which is in the local universe, of course you have a dust source, and therefore if you see it at low inclinations compared to the Fanon side. But in your high redshift sources, as you said, the dust didn't have time yet to build up, and therefore you have much larger chances to see, let's say, more from the equatorial plane, and therefore you have this kind of systematic difference to the estimation of the mass, right?
Yeah, so this may also play a role in addition to maybe actually a different geometry of the distribution of this cloud, so what we can see. So from the data that we have on the sources that I showed, that we are able to see this absorption means that this has to be within any dust sublimation radius, otherwise we would not be able to observe it. Yes. And so clearly, at least these regions are must be fairly cleared of any dust. Now in general, I think there are also studies that show that we see for the general galaxy population more dust than we expected before for many of these early sources. So how this goes together and whether we are observing fairly, let's say, galaxy poor black holes in these early times, and whether there's a difference between these populations, I think we'll need a bit more time to bring this together, these observations. But likely this dust is on the larger scales in these galaxy objects.
This dust is local to the AGN and the other, dust in the galaxy.
Exactly. Yeah.
Okay, then we have
we have an online question by Dunya. When speaking about dual AGNs, you are mentioning also simulations. What are the reasons for the discrepancy in diffraction?
Yeah, that's a good question. So sorry I didn't have time to discuss this in more detail. So for the specific case that I showed of Michele Perna's work, the difference in the simulation is about 10% or so in the fractions when we try to extract from the simulation sources in the same luminosity regime that we are observing, in the same redshift and with the same distances. If we don't try to account for all of these selection steps, then the differences are much larger. So if we just take what is published, for instance, and compare to this, then we find a much bigger difference. So this tells us that trying to take into account all of these selection effects from the observations is definitely important. And then the reason why there are still these differences is not totally clear. So of course in the simulations, in the big hydro simulations, there are often very simplified prescriptions to model galaxy and black hole mergers. Basically, when the smoothing lengths of the black hole particles hit each other, then you just merge the black hole. And often for the separations that we can observe, for instance, this other case that I showed where we see a projected 600 parsec separation, in the simulations, these black holes would have long been merged artificially. And so this is possibly one of the reasons that, that just the simple coming together and merging process depends a lot on the spatial resolution and smoothing lengths in the simulations. So this is also why this varies for different simulations. And then another aspect is whether the black holes are active or not. Because in this case that I showed, these are actively accreting black holes. This is how we can detect them. This again depends on how the accretion is modeled or how in the simulation the black holes are put into active or non-active mode. And so all of these aspects can play a role there. And we think that this is likely an explanation for the discrepancies, but in the end, one would have to look very detailed in the simulation with very different tests to find out what really brings about this difference.
Maybe one last question from Nick.
Sure. So for this model where you have a high covering fraction that's around the AGN, so that's biasing the black hole masses, how much would that affect the accretion rate measurements?
So this, you would have to talk to an expert about the accretion physics of the black holes. This I don't know. Yeah.
Okay, right. Because I guess to get these supermassive black holes, you need, one explanation is the super Eddington accretion, right? But we haven't, I guess my understanding is we haven't seen a lot of super Eddington, caught them accreting super Eddington very often. And so, I don't know, maybe this is some explanation for that.
I mean, there are a few. There are also papers that investigate this specific aspect of the super Eddington accretion in relation to the black hole masses. So there is some degeneracy which I didn't discuss, in the sense that if the more of these black holes are actually accreting super Eddington, then their corresponding masses would be lower than what we determine. Yeah? So this is also something to keep in mind. There has been at least one paper, so that I know, that tries to investigate this, which I can point out later if you're interested. And it's interesting also because the specific black hole of the resolved dynamical black hole mass measurement is highly super Eddington, factor 7 to 20 or so. And so this, this is also something that we have to keep in mind. It's possible that these geometrical factors that I was discussing and the fact that this super Eddington black hole shows this could be related, which is something that we still don't know, and we simply need more cases also of these dynamical measurements to understand better the connection between these effects.
Thank you for taking all these questions. So let's thank Hannah.